In this video, we'll look at a class of problems called related rates problems. To set the stage, let's talk about the theory of these problems. Suppose you start with an equation that relates various quantities that change over time, and you're interested in finding an equation that relates the rates of change of those quantities. Now, this sounds all very abstract, but really what we're talking about here is we're talking about functions of time. Given a relationship between functions of time, can you find a relationship between their derivatives? And the bridge here is obvious. You want to be able to take the derivative with respect to time. Now, when you deal with rates of change that are somehow related, well, we might refer to these simply as related rates. We're going to look at a bunch of problems that all have the same sort of feel. They all involve rates of change that are related to each other, i.e. related rates. Now, a couple comments are in order. First of all, the usual rules of differentiation apply. So sum rule, constant rule, power rule, chain rule, they're all on the table. Don't forget any of your rules. And you will notice throughout that implicit differentiation is going to be a critical tool for solving related rates problems. Suppose we have a rectangle and the sides of the rectangle change over time. If we call the sides x and y and the area a, there's a relationship between these quantities, a pretty obvious one. A is equal to x, y. Given that relationship, what would be a relationship between the rates of change of these quantities? First of all, notice that all of these are implicitly functions of t. We may not have an explicit formula for them, but they're all changing in time, so we should treat all of these quantities as functions of t. Now we want to take the derivative with respect to t to obtain our relationship. There's not much drama here on the left side of the equation. We're just going to have dA dt in Leibniz notation. But the right side of the equation is a product of functions, so we should use the product rule. And when we do that, we get the derivative of the first times the second plus the first times the derivative of the second. And this is going to be the equation that relates the rates of change to each other. We could do all of this using function notation. We could say a of t is equal to x of t times y of t and be sort of upfront about how these all depend on the variable t. And indeed, you could get the derivative here and it would look like this. But this route's not recommended. We're going to find out that Leibniz notation is really the way to go here. You want the flexibility of Leibniz notation, and you want to just always keep in mind that quantities could implicitly be functions of t, and you should just be ready to deal with that using implicit differentiation. You want to try to avoid using explicit function notation. Let's look at a very concrete problem. The sides x and y of a rectangle change over time. And there's a particular moment where it just happens to be the case that x is 30 centimeters, y is 40 centimeters, dx dt is 2 centimeters per second, and dy dt is negative 3 centimeters per second. So notice that would mean that the side labeled x happens to be growing while the side labeled y happens to be shrinking. Now the question is, at what rate does the area change at this particular moment? So we have a relationship between ax and y, and it yields this relationship between dA dt, dx dt, and dy dt. And let's take a moment to think about units. So y would be measured in centimeters, and dx dt would be measured in centimeters per second, which means this term would be measured in the product of those units, which is centimeters squared per second. And a similar comment applies here to this term. So that means the formula we obtained would give you a quantity that's measured in units of square centimeters per second, and that's a good thing because we are claiming that it's giving you the rate of change of area with respect to time. Now back to the actual question. There's this moment where all of that data above applies. So at that moment, we could use all this data, substitute into our relationship, and we would discover that dA dt is equal to this expression, which we can simplify, and we discover, once we put our units in, dA dt is negative 10 centimeters squared per second, and that is the answer to our problem. Let's look at another rectangle problem. Suppose the sides of a rectangle are changing in such a way that the area of the rectangle never changes. And then there's a particular moment where one side of the rectangle is 12 centimeters and it's increasing at a rate of 3 centimeters per second, and the other side's decreasing at that moment at a rate of 5 centimeters per second. And the question is, what's the length of that second side at the same moment? So let's draw a rectangle, and we will give names to the sides, and we'll call the area A, and we have our relationship between the rates of change of all of these quantities. Now, we haven't, the problem doesn't really tell us which side is which, so we have our choice here. Let's say that x is equal to 12 at the moment we care about, in which case dx dt would be 3 at that same moment, and dy dt would be negative 5, negative because it's decreasing. Clearly our job here is to figure out what the value of y is at this moment. So we need to solve for y. Now, an important clue to this problem is the area of the rectangle never changes. That is to say, dA dt is always equal to 0. So we can substitute that into the left side of our equation here. Now, if we substitute all the information we know about this moment, we find only y is left, and that's in fact what we want to solve for. And we find that y is equal to 20, and we put in our units. So the missing length is 20 centimeters at that moment. Let's try our hand at a triangle problem. Suppose the sides of a right triangle change over time. Our job is to find a formula for the rate of change of the hypotenuse. Now this sounds like a hopelessly vague question, so let's just deal with it the best we can and see where we can go with this. We'll give names to the sides. So we'll call the sides x and y and the hypotenuse z. And once we've put these names on the board, then it's clear that our job is to somehow find dz dt in terms of whatever quantities we need to use to describe dz dt. We have a relationship, the Pythagorean formula. Z squared is always going to be equal to x squared plus y squared. This has got to be true at all times because we were told that it's always a right triangle. So x, y, and z are implicitly functions of t, but it's true always that these function values are all related by this equation. And we could be more explicit about this. We could write down something that looks like this with function notation, but once again, this isn't really recommended. You should learn to use Leibniz notation. It's a lot more convenient and efficient. So dz dt, what is that equal to? We need to get from the top to the bottom here. Now, a very common temptation here is you might say, well, let's solve for z first. If we want dz dt, let's just solve for z. You don't necessarily want to go that route because you're going to gum up the works when you try to find the derivative with a square root on the right side. Turns out you don't need to do this in this case. Let's just try to go back and deal with this equation as it is. It's not that hard if we just remember how to take derivatives implicitly. What's the derivative with respect to t of z squared? So we have a power. It's a square. So the power rule tells us that this derivative should be 2z. But we're not done because z is a function of t. It changes in time. So we're going to need the chain rule. We're going to need to multiply by dz dt. We don't know what the formula for z is in terms of t, so dz dt is the best we can do, but it'll be good enough. So that's what the derivative of z squared looks like. And of course, the same kind of reasoning applies for x squared and y squared. And so these are your derivatives with respect to time here. We've got a sum rule. The derivative of a sum is the sum of the derivatives. And so here's our equation, which relates these rates of change. And of course, we can do a little simplification here. We can divide it by 2. Then we could divide both sides by z. That's a pretty good answer to our question. dz dt is equal to that blob on the right there. And it looks pretty complicated. And you know, it is, but the amazing thing is we were able to find it quite easily from the original relationship z squared equals x squared plus y squared. Let's look at a different kind of triangle problem. Let's suppose you had one of these ladders that can collapse and extend. And let's suppose you have that ladder lying up against the side of a house. And it starts sliding down the house. Maybe the base kicks out, the ladder's collapsing, all sorts of stuff's happening. Suppose at a particular moment, however, that the bottom of the ladder is 3 meters from the building, the top of the ladder is 4 meters from the ground, the bottom of the ladder slides away at a rate of 0.02 meters per second, and the ladder's collapsing at a rate of 0.08 meters per second. So there's a lot of stuff going on, and we want to figure out at that particular moment how fast is the top of the ladder sliding down the building. Wow, okay, a lot of stuff's going on, but if we're careful about this, we can keep everything organized and it won't be so bad. First of all, let's get some names for the quantities. So we're going to label the sides x and y, and we'll call the hypotenuse z. And we're going to translate all this information into more succinct mathematical notation. So the bottom of the ladder is 3 meters from the building, so that means x equals 3. Top of the ladder is 4 meters from the ground, that means y equals 4. The bottom slides away from the building at 0.02, that means dx dt is 0.02, and if the ladder's collapsing, dz dt should be negative 0.08. Why negative? Because z is decreasing, the ladder's collapsing. So dz dt should be negative. Now at that moment, we're trying to figure out how fast the ladder's sliding down the building. What we're really asking is, what is dy dt at that moment? So let's head back to our fundamental relationship, z squared equals x squared plus y squared, Pythagorean identity. Now, here's another common temptation. You might look at all this information on the board and you might say, hey, x is 3, y is 4, so let's plug those in. That means z is 5. Let's take the derivative, and you get 0. But something's really wrong here because we were told that dz dt was negative 0.08. So these don't match up. Something went wrong. What went wrong is we tried to substitute 3 and 4 for x and y before we took the derivative. X equals 3 and y equals 4 only at a particular moment. It's not always true. So you can't take the derivative based on information that's only true for a moment. So what we might say here is, don't substitute transient information before taking the derivative. If it's temporary information, it only applies to a fleeting moment, don't plug it in before you take the derivative. You got to take your derivative first. So we'll go back to the top. Here's our Pythagorean identity. We'll take the derivative, do the simplification. Here's our relationship. Now at the moment in question, we can plug in what we need to, and we obtain this equation. Now we're looking for dy dt, but there's still one piece of data missing, and that is z. But at the moment in question, it is true that z is 5, so we'll substitute that in, and now we're in the home stretch. We can simply work our way through this, and when all the dust settles, we find that dy dt is negative 0.115 meters per second. You could switch units, it's the same as negative 11.5 centimeters per second, but that's the rate at which the top of the ladder is sliding down the building. So let's summarize our thoughts about working with related rates. Find an equation that relates variable quantities that you care about. Don't use transient information yet. Take the derivative with respect to time. Now plug in all the information you were given to analyze the moment in question. Generally speaking, this collection of principles will help guide you through most related rates problems.